Hi, in this video, I'm going to give you a new framework to understand hypothesis tests. So let's start from a typical model. Like suppose that your model, your econometric model, is parameterized by theta as usual, and the parameter, true value of the parameter satisfies this condition. So there is a criterion function Q0, and your true parameter minimizes the criterion function. And we assume that, so you need many assumptions to define this kind of criterion function. You may think about the classical linear regression model, and Q is the least squares criterion function, or MLE, or GMM, whatever you want. Anyhow, you need assumptions to have this identification result. This is the identification result. And here, this is your model, and we assume that the assumptions so far are correct. On top of this, you are wondering whether this is correct or not. So the hypothesis will be written in this way, which means theta 0, the true value of theta, satisfies this equation. So there is a function R, which I will call a restriction function, a restriction. So under this restriction, the true value should make it equal to 0. All right, for example, if your null hypothesis is beta plus gamma equals to 1, the restriction will be beta plus gamma minus 1. Then it equals to 0 if the hypothesis is correct. And if your assumption is beta 1 greater than beta 2, then you may define the restriction in this way: minimum of beta 1 minus beta 2 and 0. So if this equals to 0, that means this is greater than 0. And if your null hypothesis is exogeneity of the instrument, then your restriction will look like this. Your restriction is an expectation. So any kind of hypothesis can be written as like this. Of course, the function R may be a vector. If you have more than one hypothesis, more than one equality or inequality, then you may extend the restriction function. As you can see, you may use many different types of function there. And then this is your hypothesis, but we did not utilize the hypothesis in this identification. So you have to, for your hypothesis to be tested, you should be able to identify the parameter first and then check if this identified parameter satisfies this or not. You know the restriction function, and then the remainder is to find theta 0, which is possible by this identification result. Or you may understand it as the hypothesis test is another assumption. Right? The hypothesis itself can be another assumption. So using that idea, you can define two different models. One is a restricted model. So this is the restricted model. So which means if you add this restriction onto this minimization problem, you are going to get a different theta. So theta R is restricted value of theta. So that means you are minimizing the criterion function subject to R theta equals to 0. So you believe that the restriction is true. So you are using this when you estimate the parameter. That is possible. And so what I'm saying here is, without this hypothesis, still you can identify theta, but you may utilize the hypothesis if you believe this is true. Or you may have a totally different criterion function if this is true. So for example, if the instrument is true, then your criterion function may have an additional instrument, so the criterion function itself could be different. Anyhow, so we call this the restricted model. So we use the hypothesis as another assumption in your estimation or in your identification. So it is closely related to over-identification. Think about this. As I said, you must be able to identify the parameter without the null hypothesis. Otherwise, you cannot test it. So the main idea is you have to identify the parameter and then see if the parameter satisfies your hypothesis or not. That is how you test the hypothesis. If you cannot identify the theta 0 without the hypothesis, then you cannot test the hypothesis. Then now, now if you interpret the hypothesis as an assumption, then your model becomes over-identification. You can identify the parameter without using the hypothesis, but if you include your hypothesis into your model, then you have an extra assumption which is not necessary for your identification. So your model is over-identified. Over-identification is like conceptually it's an over-identification situation. And think about the example. So suppose that you would like to test whether X is exogenous or endogenous, but this is not testable. This is not testable because without this assumption, you cannot identify the classical linear regression assumption. You cannot identify the classical linear regression parameters. So this is not testable. To test it, if you want to test it, you need to include another assumption which enables you to identify the parameter. So instead of this assumption, you have to have another assumption so that you can identify the parameter. The example is instrument. If you have an instrument, then you can identify the parameter using the instrumental variable regression method, and then you can test whether the X is exogenous or not. Second, example 2, full rank assumption. It is testable because, and this is a little bit interesting, the full rank assumption is testable because it does not include the beta. So it does not depend on unknown parameter. So without this hypothesis, you know everything related to this hypothesis. So this is testable because you can calculate expected value of x prime without any other assumption. Now, calculating expectation does not require any assumption. And example 3, similar to the first example. You would like to test an instrument, whether an instrument is valid or not. For this to be testable, you have to have over-identification condition. So, for example, when you have one endogenous variable and you have two instruments for one, then you can test one of the instruments. So, however, if you have one instrument for one endogenous variable, then you cannot test anything. So you don't have any over-identification assumption, then testing is not possible. So then, extending these ideas more and more, we may think about different models. So earlier, at the beginning, earlier this semester, I said an econometric model is a set of assumptions. What kind of assumptions you use, depending on the assumptions, your model may be different. And then you may compare different models. One model may use more assumptions than another, or one model may use fewer assumptions than another. So by comparing their assumptions, you can compare which model is more restrictive, or which model is more general, or which assumption is milder. So then you can think about the hierarchy between the models. For example, classical linear regression model is more restrictive than instrumental variable regression model. So you may understand the classical linear regression as a special case of instrumental variable regression model using X as an instrument itself. So the instrument for X is X. Then you get the classical linear regression model. So the classical linear regression model is a more restrictive assumption model, and the instrumental variable regression model is more general model. So, and in this case, we say classical linear regression model is nested by instrumental variable regression model. So it's nested. So it's just a special case. And similarly, as I explained earlier, when you think about testing hypothesis, you can using by including or not, like including the hypothesis or not into the model, you can think about two different models. Unrestricted model is the model you do not use the hypothesis. So I don't care about the hypothesis. Still, you can identify the parameter. But restricted model uses the additional assumption in the hypothesis test, in the hypothesis. So null hypothesis becomes another assumption. So it uses more assumptions. So it is more restrictive. So it is nested. The restricted model is nested by the unrestricted model. It's a special case of the unrestricted model under the case where the parameter satisfies the hypothesis. So we will consider unrestricted model this way and restricted model in this way or this way. So depending on the formulation, you may need to change between them. Here's example. Variable selection. So it's continued from the earlier examples. Variable selection, you wonder whether x2 is relevant or not. So you want to see whether x2 should be included or not. Then the idea is estimate both. Estimate the model including this or not including this. So, and the model not including x2 is more restrictive because this model is a special case of the unrestricted model with beta 2 equals to 0. So when beta 2 equals to 0, the unrestricted model becomes the restricted model. So the restricted model is a special case, and so nested by the unrestricted model. And you may consider a criterion function like this and restricted criterion function like this. Functional form test, example 2, general unrestricted model, fourth order polynomial, restricted model is linear and simple. So you know we are imposing beta 2 equals 0, beta 3 0, beta 4 0 on the unrestricted model, then it becomes the restricted model. So nested. And combination of parameters, restriction on the combination of parameters, Cobb-Douglas function, then unrestricted model, beta and gamma can be anything. But restricted model, you believe that beta plus gamma is always 1, then replace gamma with 1 minus beta. So using 1 minus beta instead of gamma, this is a special case, so it's nested, and you can naturally define the restricted criterion function this way. It does not have gamma at all. So gamma disappears from the criterion function. Inequality restriction. The problem here is inequality is a little bit different from the equality restrictions. Inequality does not have a restricted model because it does not specify one specific value. So this is a little bit, however, still, even though there is no restricted model, you may understand the restricted model in this way. So there is a constraint. The constraint is on inequality. And the problem here is the inequality may be binding or may not be binding. And depending on that, the model may be different. So that's why there is no fixed, one fixed restricted model. And example 5, exogeneity test. Exogeneity test, restricted model, x is uncorrelated with epsilon. Unrestricted model, x and epsilon may be anything, but we assume that there is another instrument z. So of course, instrument z is included in here, but it is not important in the restricted model. Not necessary. And then if without restriction, you have to use z only, but under the restriction you need to use x and z at the same time. However, if you do the math, z is not necessary, because if you have x, then you don't need any other instrument. So if x is exogenous. So this is another example. And example 6, over-identification test. Usually when we say over-identification test, this is a test for the validity of an instrument. So restricted model, the unrestricted model uses only one instrument, but restricted model uses two instruments. And we are testing this. So using this equality or not. So depending on this, we would like to see whether Z2 is uncorrelated or not, exogenous or not. And so unrestricted model uses one instrument, but restricted model uses two instruments. That's the difference. So far I explained hierarchical models, but of course there are non-hierarchical, non-nested models. For example, linear model and linear log model. There is no nesting relationship. It is not like neither is more general than the other. So, but there is the literature. There is different theories, different methods you can apply to compare to non-nested models. But we do not discuss the theory in this course. From now on, we are going to consider hypothesis testing, and the hypothesis testing may be understood as comparison between two nested models, restricted or unrestricted models. Okay, I will stop the video here and continue in the next one.